Afternoon, 61C. Bit louder. Afternoon, 61C. That's better. Okay. So, you should be excited because today we're changing topics. So no more MIPS assembly code for today. I know that's your favorite topic, but we're going to move on down into the guts of the machine. So, MIPS assembly code is where the software ends. That's the final part of software down to the machine code. Those bit patterns in memory, hardware is going to execute those. And so the next few lectures, what we're going to go through is how you build computers for real. So we're right down this bottom level. We're going to start from very simple switches and gates and build all the way up to a functioning computer that can run those programs you've been writing. So hardware design. We're going to be talking about how a processor is built from building blocks, and to manage the complexity, we're going to build things up from the bottom up and build bigger components that will eventually plug together to build a whole computer. And these days, a question you might have is, why do I need to study hardware design? Those guys at Intel seem to have got that covered, or those guys at Qualcomm or Apple or whatever. Well, even if you never get to design hardware, if you don't understand how it works, you'll never be able to extract the full potential out of the chips you're using. So even if you're only a mere software developer, you have to understand how the hardware works if you really want to extract peak performance, peak efficiency. And this is true whether you want to build a very tiny, Internet of Things that your device or your next startup, you want to figure out how to squeeze the most out of a few gates. Or if you're programming, as you will be doing in the last project, a whole cluster of machines in a warehouse, you really want to understand how the thing works so that you can get the most out of it. So understand, we're going to teach you how hardware is built. You'll figure out what processors can do fast and what they cannot do fast. So don't do the things they do slowly. And if you actually do want to get into hardware design, it's a very there's constant demand for top engineers in hardware design. They get paid a lot more than the software developers do because it's harder. That's why it's called hardware. Software, hardware. There's a reason for those terms, right? Hardware is harder. And if you want to follow up and actually work in this area, there's some upper division classes, CS150 and 152. 150 is more on the digital logic design, and 152 is more deeper into computer architecture, how you build computers in particular. Another thing is things are going to change. We're at the end of Moore's Law, and you're just starting out on your career. So next 30, 40 years, something else is going to come along, and who knows? This hardware stuff may be extremely useful for whatever the new device is going to show up in the next 30 years. If you don't understand this generation of hardware, you'll get completely lost with the next generation, right? Another trend that's happening, because Moore's Law is ending, there's actually a big upsurge of interest in hardware design, even at what you might consider big software companies. So places like Google are designing custom hardware. Companies like Apple are designing their own chips. Lots of companies are doing specialized chips themselves because they can't just do it in software and a regular processor. They have to build some custom thing to hit that capability that really differentiate them from the other guys in the market. So custom hardware design is becoming increasingly a thing that's going on even at surprising places. So Microsoft, for example, is deploying field programmable logic gate arrays inside their servers to run the Bing search engine because they can get about a 2 to 3x efficiency increase by having some programmable hardware gates inside their regular servers. So this is a trend that's happening right now. So more and more hardware design is sort of coming back into the mainstream. Okay, so when you want to design a computer system, let's go all the way down to what's the basics here. So the basics are all the computers that we're interested in, we're going to be building are examples of what we call synchronous and digital systems. Okay, so let's go through those terms. So a synchronous system is a system that's guided by a clock. So there's a global clock tick, and that orchestrates all the behavior in the system. So everything moves according to the beats of this clock. And when you buy a laptop these days, I guess these days you may not care about it, but there's a number attached to the processor, which is the rate at which it's guaranteed to be able to run at. So for example, you might have a 1.9 gigahertz processor in your laptop or a 3.2 gigahertz processor in your desktop. And that's the speed of the clock that's synchronizing the fastest part of the machine. right? That's beating away. Digital, what do we mean by a digital system? Well, a digital system is one that has quantized levels or digits representing the state, as opposed to an analog system. An analog system would be like, some voltage value would encode a value. In a digital system, there's discrete steps, and those are the digits. And in particular, in all the systems we work with today, there's only 2 digits, 1 and 0. So everything is binary. And so zeros and ones are the 2 values any signal can have. And there's many advantages to that in that you can reliably generate ones and zeros, and you can easily remove noise by telling if it's above or below a certain value, is it a 1 or a 0. And so there's many reasons why we use binary in our systems today, but all of our systems are synchronous and digital, the ones we're going to be talking about. And even the processor is going to be synchronous and digital. So let's go through basic, hopefully high school physics on how you connect batteries and switches and light bulbs. So if this is a battery here, and this is a light bulb, and this is a switch, right? This is showing the switch open. When the switch is open, no current can flow. So the light bulb is off. When I press the switch closed, I complete the circuit, and current can flow around this loop and light up the light bulb. So if you think about what the functionality of the circuit is, it's when the switch is on, the light is on. So light bulb on, which is Z, equals switch being closed, which we call A, right? So if the light switch is closed, the light bulb's turned on. Switch is open, light bulb turns off. Pretty simple. I'm sure you've all done this many, many times. Okay. But now you can have more complex functions. So we can compose those switches to make logical operations. So if I have 2 switches in series now, I will only make a circuit if both those switches are closed. And that's called an AND operation, right? So if A and B are closed, the circuit is made and the light bulb will turn on. I can do other ones like OR. If A or B are closed, the light bulb turns on, right? These are 2 different logical operations, right? So here, when it doesn't matter which one is on or if both of them are on, in either case, the circuit will be made and current can flow through here, right? So these are some simple examples of Boolean functions. And it doesn't really get much more complicated than this in order to build a complete computer. This is the basic of all you need to know. So this idea, we're going to teach you a very systematic way how you build computers, but when people first started out, they didn't really know what they were doing. It's usually true when you start engineering in a new field. The engineers just blast ahead and build whatever, and then later on, theory follows on, filling in, well, this is what those guys were actually doing. Similarly here, where the early computer designers just built their own funky circuits using switches, but then they started to notice useful common patterns showing up in their work and how things were put together. And so this fellow, Claude Shannon, he made this link between the kind of computer engineering work that was going on, very early engineering work, and this 19th century mathematician, George Boole, who, as is usual with mathematicians, they come up with theory that nobody understands why it's at all interesting. Why would you ever use that? And then a few hundred years later, the application pops up, and lo and behold, you're glad they did all that work, right? And so they named this kind of logic Boolean logic, and this mathematician already invented a lot of theories, did a lot of work in that area when it was purely abstract. He didn't know what the application would be. After the computer engineers have been building these things for a while, Shannon made this connection. Oh, that's the same as what this guy had been talking about a while ago, right? And that's why we call it Boolean logic in honor of George Boole. And so we can use his math to help us simplify our logic designs, make simple circuits using less switches. So computers are built out of switches, and this is the key element you need to make any kind of digital computer, is a switch, and in particular a switch that can be controlled by other switches. So you need a switch where, whether it's on or off, isn't a human standing there flipping it up and down, but some other signal in the machine can turn that switch on and off. So it's a 3-terminal device. There's the 2 things you're connecting, and the control terminal that says whether they're connected or not. And once you have that, you can build any computer. And in our modern computers today, those switches are transistors, and in particular, CMOS transistors. We'll go into what that means in a minute. And in our modern computers, we use voltage to represent high and low, ones and zeros. So a high voltage represents a 1, a low voltage represents a 0, usually. And the low voltage is the ground point of the system. The convention is a ground at the bottom, the voltage scale. And the high voltage is the power supply. It's called VDD, voltage that goes to the drains. And in modern microprocessors, it turns out VDD is about 1 volt. So in most of your laptops, your smartphones, your tablets, the power supply is, give or take, around 1 volt is where the logic actually operates. All those transistors are switching around. The nice thing that's mentioned here as well is if you feed a signal in to a logic gate and it's not exactly at 0 volts and it's not exactly at 1 volt, there's some switching threshold. And if the signal is above that, it's treated as a 1. If it's below that, it's treated as a 0. And that value is then recreated on the output of the logic gate. And so you remove noise. So as the signal moves through the system, noise is removed. And that's why digital systems are so reliable, even though we have billions of transistors in these chips. It's basically digital means you can get rid of noise. That's why we don't have analog computers these days. Okay, so our modern transistors are CMOS, which stands for complementary metal oxide on semiconductor. And the complementary means that there are 2 kinds of transistor. The kind of the negative of each. One's the joule of the other. So one is, as we'll see, one is on if the control terminal is a 1. The other one is off if the control terminal is a 1. Right, and there's what we call N and P type transistors. So we have 2 kinds of transistor, and that's why it's called complementary. MOS is metal oxide semiconductor, and that's actually 3 layers in the construction of the transistor. The control terminal is on metal these days, and that's called the gate, and that's metal. And it's insulated from the channel by an oxide, and the channel is made from semiconductor. So this kind of sandwich of metal oxide semiconductor is at the heart of a modern transistor. So complementary metal oxide semiconductor transistors, CMOS. So these are the dominant types of logic we use today. And they actually work very similar to relays or even those light switches. There's a control terminal that turns a switch on or off. And the nice thing about CMOS compared to some other technologies, it only really uses a lot of energy when you switch. So if a circuit is stable, it doesn't take a lot of power. It's only when it's actively doing something, it takes some energy. So here's a picture of a simple schematic of a CMOS transistor. We've just drawn it like a switch. So we call the 2 things that are connected, the source and the drain. They're actually really the same. There's one's by convention called the source, one's called the drain. Physically, they're the same thing. It's just which one's connected closer to the power supply is where you call one the source or the drain. And then there's the gate, which is the terminal that controls the switch. Okay. So in a regular transistor, this is a circuit symbol for it. This is a schematic just to show you how it looks like in a switch. But the circuit symbol looks like this. Right. When a voltage is applied to the gate here, it actually pulls carriers into the channel and makes this connection, which is why it's drawn like this. I said there was 2 kinds. This is an N-channel transistor. An N-channel transistor, when the gate voltage is a 1, the source and drain are connected. When the gate voltage is a 0, they're disconnected. Okay. The other type is called a P-type transistor. And the only difference in the drawing is there's now a bubble here. And that bubble signifies inversion. So for a P-type transistor, when the gate is a 1, the circuit is disconnected between source and drain. And when the gate is a 0, they're connected. So this gate works the opposite way around to this gate. So that's the primary functional difference between the N and the P. And as we see, that lets us build some very nice circuits. There are a lot of detailed differences. You don't have to worry about this too much in this class, but just so you'll understand why we build things a certain way, if you want to go into this a bit more deeply. The N-types are good at conducting zeros through here. The P-types are good at conducting 1s through here. And so we can't use them quite interchangeably like you might think. We'll get into that in a bit. All right. But the thing you have to remember, N-type, gate is 1, thing is connected. If it's 0, they're disconnected. On a P-type, it's the opposite. Gate equals 1 means disconnected, and gate equals 0 means connected. But they're just switches. They're just electrically controlled switches. Now, the great thing about these CMOS transistors is we know how to build lots of them, and lots and lots and lots of them on a surface of a chip and connect them together. And, this is the basis of Moore's law, one of the great ideas. So what Moore figured out was, looking at the first few years of integrated circuits, he figured out for every generation of circuit technology, what was the most cost-effective number of transistors to place on a chip, right? Taking into account, if you tried to put too many on, they wouldn't all yield and you'd get failures, right? If you put too few on, you would waste money. So he's figuring out what's the most cost-effective number of transistors per chip in each technology generation, and then he extrapolated how he expected that to advance over time, and he was surprisingly accurate that, over this long period, we've basically been doubling every 18 months to 2 years, doubling the number of transistors per chip. And we've been doing that for a long time, and so now we're at literally billions of transistors on one chip, billions of logic transistors on a single chip. And actually, I think we ship something like, I can remember the exact number, 10,000 to 100,000 times the number of ants as transistors every quarter. So we manufacture that many transistors. It's far more than the number of ants on the planet, right? So we're very good at building these things. Just to show you, I thought it'd be fun to show you some modern technology. This is Intel's 14 nanometer technology. They just started shipping this in their Broadwell chips. And what you're seeing here is so these chips are built on these big wafers, and you're looking down at a blow-up of zooming into one chip and just a few transistors on that chip. And these are the various contacts that are being made to pieces of transistor. And these are just a couple of metal layers. And here's a distance scale. So this is 700 nanometers from here to here. You can see how tightly packed in these transistors are. So the transistors themselves are amazing, but what's more amazing to me is they can all be connected together in an arbitrary pattern on the chip using layers of metal. So this is looking down on the surface of the wafer, and you see the transistors laid out. Now we're going to take another look take a cross-section through and look at the layers of wiring that are on top of the transistors, and they look like this. So the transistors are down here at the bottom, right down here at the bottom, these tiny dots. And what you're seeing here is there's 4 layers of metal here, another 2 here, another 2 here, another 2 here. 10, 12 layers of metal, very thick metal at the top that carries the power around. And all these other layers of wiring, how all those transistors are connected together. And what's amazing to me is we can now fabricate, a chip that has like 1 billion transistors on, clocks at a couple of gigahertz. They're all reliably connected through these wires, and you can sell it for a few bucks, right? So that's the amazing thing about this fabrication technology. The sad part about this is not going to get much better than this. We've only got a few generations to go before we hit sort of atomic limitations on how small we can make things. But what's also incredible, notice how cleanly patterned these are. Like the corners are square and everything's really nicely laid out, even though it's these tiny, tiny, tiny feature sizes. So this is the miracle of modern process technology. Anyway, so these transistors are very, very tiny, but that's all there is on these chips. Everything, the processors, the memory, everything on the chip is made out of these transistors. That's the only component, plus the wires that connect them together. And you make complete computers just out of those simple transistors, the 2 I showed you, the P and the N transistors, makes everything on a modern chip. So I mentioned some of this briefly. These are just some rules that will explain why the gates are built the way they are. You don't really have to memorize these, but basically N-type transistors are not very good at passing ones, but they can pass a strong 0. And the opposite is true for the P-type. They can pass weak zeros but strong 1s. And so the reason we build complementary logic is that one side kind of counteracts the other's weaknesses. So we use both types of transistors together to get circuits that can pass 1s and 0s that are both strong onto the next stage. So we need both types to get good circuits. It's very important that you always drive a wire. You never leave a wire just floating. So a wire should always be connected through some set of closed switches to power or ground. And we should never directly create a path that shorts the power supply to ground, because that will just collapse the rails and the chip will stop working, right? If you actually connect power to ground directly, it's a bad thing to do. Okay, let's try building some very simple logic networks using these transistors. So here's just 2. So here's a P-type transistor, right, and an N-type transistor. And on this terminal, I'm attaching 1 volt, the power supply. On this terminal, I'm attaching 0 volts, which is ground. And the question is, as I change the value on this control terminal X, which goes to both this gate and this gate, what does this output node Y do? Okay, so if I put 0 volts on X, what happens to Y? All right, let's first go through this. So I'm putting 0 volts on the X input. So this transistor, is it on or off if I have 0 volts on X? It's on, right? So P-type, you can see by that bubble. The bubble means you invert it. So if this is a 0, this guy's actually on. So if this guy is on, it means there's a connection from here to here. Okay, what does that mean about this voltage? It's going to be 1 volt, right? Okay, but let's check what's happening down here. So on this transistor, is it on or off? On or off? It's often on off, right? That's what I hear. Okay, no, this is off, right? At 0 volts on an N-type transistor, that transistor is off. What that means is there's no connection here. So this node Y is being connected through to the power supply through this path. So 1 volt is appearing out here. So when this is 0 volts on X, you're going to get 1 volt. I did the wrong one first. Okay. And guess what? When you change X to be 1 volt, this guy switches off, and this guy turns on. So now Y is connected to the ground rail. So now Y is a 0. So 0 volts on X turns into 1 volt on Y. 1 volt on X turns into 0 volts on Y. So what have we just built? A NOT circuit, right? So this inverts a bit. So you have a bit, comes in as a 1 or a 0. It leaves as a 0 or a 1. We've inverted it. So this is a very primitive logic function. This is an inverter, right? And that's how you build it. Just 2 transistors connected this way, and you built a logic gate. A couple of things to note here. This output value is being driven from this power rail here, right? So this 1 volt is being pushed through here, not from the input, right? So the input doesn't directly couple to the output. It controls these 2 switches, but the actual current and everything is flowing from the power supply here to the output, not from the input to the output, okay? And that's a powerful thing. It means that we don't load the input when we're driving other gates, because it just controls the other switches, and the power actually comes from the power supply directly. So you get a clean 1 or a clean 0 coming out of here, even if this is a little bit noisy and it's not exactly 1 and not exactly 0. Anyway, so that's our first logic gate, just built with 2 transistors. Let's get a bit fancier now. Let's build a little bit more complicated logic gate. So now we're going to use 4 transistors, and this logic gate is actually going to perform a function of 2 input variables. So I have X and Y coming in. When I have 2 inputs that each can hold a binary value, 0 or 1, I have 4 combinations, right? So I'm going to go through all 4 combinations to see what does this circuit do on the output here, what appears on Z. Okay, if X is 0 and Y is 0, first of all, if X is 0, what does that mean? Is this on or off? It's on. So if this is on, it means these 2 are connected, so 1 volt will appear here. Okay. What about this guy? That's off, right? So this is off. So to understand what's happening here, let's check Y. So if Y is 0 volts, what does that mean for this transistor? This is also on, and this one is off. So these 2 are off. So there's no connection to 0 volts. That's good, because both of these are on, and so both make connection to 1 volt. Is it a problem that both of them connected to 1 volt? No, it doesn't really matter. The potential, this is 1 volt here, 1 volt here. It's fine that both of these are connecting you to 1 volt, right? So this is just like that OR circuit we had before. At least, so when X and Y are 0, what is Z? It's 1 volt, right? So when X and Y is 0, you get 1 on the output, 1 volt. What if X is 0 and Y is 1? So if X is 0, this guy is on and this guy is off. But Y now, this changes, right? So what happens? So this one is now off, and this one is on. What is the output? Who thinks it's 1? Okay, who thinks it's 0? And the rest of you are not thinking, right? All right, so what happens is when you switch y from 0 to 1, this guy turns off, this guy turns on. This guy turning on doesn't really change anything because this guy is off. So there's no path to 0 volts, right? This guy turning off doesn't change anything either because X is still on, this gate is still on, and this is connected to 1 volt. So this stays at 1 volt, okay? Now this next case is just symmetric with the last case. Now I turn X to 1, but put Y back to 0. And so we actually get the same pattern here. Now this guy is, this is off, but this is on. This is on, but this is off. So Z, the only path to a power supply is back this way, to 1 volt. So Z is still 1 volt. The final case is interesting now. When both of them are at 1 volt, right? So both of these guys are off, and both of these guys are on. And so now what's the output? 0, right? 0 volts on the output. So what kind of logic function is this? Not and, right? It's not an and. So if you invert this, it's an and, but then you invert the output of an and, right? So if X is a 1 and Y is a 1, if it was an AND gate, you get a 1, only in that case. But in this case, you get a 0, only in that case. So it's not an AND gate. It's the result of an AND gate, but inverted, right? Okay, so this is how you build a logic gate. It turns out that you could actually build everything in a computer using just NAND gates. If you just took this, many versions of this, you could build any computer you could imagine. Yep. Good question. The question was, if you got a 1 and a 0 both going to Z, what would happen? The answer would be you'd be connecting the power supply, you'd be shorting out the power supply, and your chip would fail. So you have to design the circuitry such that it can never be the case that, given the combination of singles, the 1 volt connects directly to the 0 volt. That should never be allowed. And you see that's been engineered for the design of this gate, right? So the only time that Z connects to 0 if X and Y are both 1. If X and Y are both 1, both of these gates are off. So that's part of the trick of designing these gates. You have to design the gates in a way that there's only one path to one of the power supply rails to the output. There should never be a path from the output to both supply rails at the same time, because that would mean they'd be shorted together. And so this is part of the trickery designing these transistor networks. I think my computer just crashed. Okay. It's okay, I'll reboot. It's just... Okay, right back up. Oh, it's clicker time now. So here's a different logic circuit. So you basically have to say, what does this one do? So there's 4 choices, A, B, C, or D, over in the right-hand side. So figure out what's the right combination of outputs that this circuit will generate. Okay. Okay, about to wrap this up. Let's see what people thought. Okay. So there's a clear front runner here, but let's give you another couple of minutes just to convince your neighbors. Okay, so, yep. Okay, everybody picked C. That was the right answer. Whoever picked E, that was not the right answer, clearly. Okay, so you see here that when in C, the only time that the output is a 1 is if both x and y is 0. Only when x and y is 0 is these both on and 1 volt connected to the output. All other cases, one of these two is off and one of these is on, giving you that pathway. Kind of notice that when we build these circuits, the what we call the pull-up network, which is the network that connects you to the positive rail, is always complementary to the pull-down network that connects you to ground. So only one of those two pathways can be on at a time. The thing that pulls you up to 1 volt, the thing that pulls you down to 0 volts. So notice always that you put the P-type transistors are in the pull-up network that pull you up, and the N-type transistors are in the pull-down network that pulls you down, because the P's are good at passing 1s and the N's are good at passing 0s. That's why we draw the gates this way, design the gates this way. Okay, let's go to a bit of administrivia. So project 1 is out, due March 1st, but get started on that. Don't wait until day before. If you still don't have a team member, come down to the front and see Sagar at the end of lecture. Then we'll do the pairing right here. You should have done that beforehand, but if you don't have a project partner, come down here at the end of lecture. We have the first midterm is coming up next Thursday, and that'll be in class. So that covers everything up to the previous lecture. Okay, so not today or anything after today in lecture, but covers everything up to the previous lecture. So all the, if you ask me what's on the midterm, it's everything up to including the previous lecture. You're allowed to have one 8.5 by 11 double-sided written cheat sheet. We'll give you the MIPS green sheet, so you don't have to memorize the opcodes and the encoding. We'll get that to you. Sago should have talked to all the DSP students, and you have to come back to us by tomorrow, midnight, for accommodations, okay? All right, any questions about any of this? Yep. Sorry, was the question, is there going to be a review? Will there be a review? Review sessions? As if by magic, yeah. So that's when the review sessions will be. Any other questions? Sorry, say again? Sunday is the 22nd. It should say Saturday. Okay. What's Northwest Genetic Plant Biology? Okay, we'll write this up on the website. Look on the schedule on the website for the full directions. Okay. Okay, any more questions? No, okay. All right, let's keep going. So we've sort of shown you how to build these little building blocks. Just putting a few transistors together, we can build an inverter, a NOT gate, or a NAND gate, or a NOR gate. The last thing we showed in the clicker, this is actually not an OR gate. It's a NOT OR, right? An OR would be if X or Y is a 1, the output is a 1. In this case, if X or Y is a 1, the output is a 0, else it's a 1. So this is actually a NOR gate, which is short for NOT OR, okay? So when we do logic design, we use these symbols to represent these standard components. And this is the symbol for a buffer, which just copies input to output. But the bubble on the output means it's inverted. So an inverting buffer looks like this. It's a triangle with a bubble on the output, right? So this is a NOT gate. An AND gate looks like this with a flat back and a rounded front, A and B going to Z. A NAND gate, which is not an AND gate, is the same except there's a bubble on the output. An OR gate has a curved back like this and goes to a point. That's an OR gate, and if you have a bubble on the front, that's a NOR gate. So these are the classic schematic symbols for those three type of logic gate. It turns out that in our technology, in CMOS technology, inverting versions are easier to build than non-inverting versions. So NOT, NAND, and NOR are actually the building blocks in modern CMOS technology, all right? And you should see that from the way those pull-up and pull-down networks work. The P-types, when the input is a 0, they turn on. And the P-types are the thing connecting you to the plus 1 volt rail. So when the input's a 0 is when the pull-up network is connecting you to a 1. And similarly, when the inputs are a 1, you turn on the N-type transistors, which are in the pull-down network. So when the inputs are 1, you're being connected to the 0 volt rail. That's why the inverting versions of these gates are the natural things to build, right? So inputs come in as a 1, the outputs tend to be a 0, right? If you want to build so how do you take one of these gates, do you think, a NAND gate, and make it into an AND gate? You can use 2 NANDs. What's a cheaper way of doing it? A NOT gate, yeah. You can take a NAND gate and put a NOT gate on its output, and then you've got an AND gate, right? And the nice thing about this technology is that each stage kind of buffers the signal electrically, because at each stage, the inputs are connecting the output to the power supply. And so you kind of get to start over again being driven directly from the power supply. And so it's easy to chain these logic gates together to build very deep circuits that all function correctly, right? And actually, in this technology, if somebody gives you, a design of an AND gate, what it will be is actually a NAND followed by an inverter. That's the best way of making an AND gate in this technology. Okay? So, when we want to build some logic function, so these were standard ones, NAND, NOR. When we want to build some other function, the way we start out as designers is filling out the truth table, what's called a truth table. What the truth table is an exhaustive listing for every value, every combination of the input values, what should the output values be, right? And so if you have some logic block here that has 4 inputs and 1 output, how many combinations are there of input values? 4 inputs that are binary, how many combinations? 16, right? 2 to the 4. So there are 2 to the 4 rows in this truth table, and for every one of those, you need to write what is the correct output value, right? So it's kind of showing here as some function of those 4 inputs, right? Okay, let's try and build this. Look at this example. So this is a truth table for a very simple logic function, and this tells you if the output is a 1, if A is not equal to B, right? So if A and B are both 0, the output is a 0. If A is a 1 and B is a 1, the output is 0. But if they're different, then you get a 1 on the output, okay? Now, the way you write this in algebraic form is kind of cumbersome to always write out these big truth tables. There's sort of standard ways of writing out logic expressions, and this is an example how you would do this here. So we're going to say y equals this expression, and what this really says is y will be a 1 when, the value of y will be given by this logic expression, right? This first term here is AB, but notice there's a bar above the A. That bar is our algebraic notation for a not. So that means not A. So not A. This looks like A and B. If you're thinking about math, this looks like they are multiplied together, AB. And that product is what we use to express an AND operation. So if not A and B, i.e. if A is 0 and B is 1, this whole expression is a 1. Over here, if A is 1 and B is 0, that means not B is 1. So if A is 1 and B, not B is 1, this whole expression is a 1. So if either this is true or this is true, the plus means or, right? So product is like an AND, the plus sign is like an or, and that's how you write out the logic function symbolically, right? And it turns out this is another standard gate we call an exclusive OR gate. So in English language, when we say OR, we usually actually mean the exclusive OR. But in logic, you mean the inclusive or, right? So we say you can either do this or that, but not both, right? That's the exclusive OR gate. Either A is on or B is on, but not both, right? That's an exclusive OR function, right? Let's do another example of a truth table. This is for an adder. So now, all the arithmetic operations you want are just combinational, are just these functions of their inputs, right? So if I have a 2-bit input where A0 is the low bit of the A side and A1 is the high bit, similarly for B0, B1, if I add two 2-bit numbers together and I want to get an output that doesn't have an overflow, I'm going to need 3 bits to represent the output, right? Because what's the biggest number I can hold unsigned in 2 bits? 3, right? So 3 plus 3 is... That was hard. 3 plus 3 is... Okay. And how many bits do I need to hold 6 unsigned without overflow? 3, right? So I need 3 bits on the output. But these are just bit patterns. So the truth table, the way you do with logic doesn't care that this is an adder. All it needs to know is what are the input combinations, what are the output combinations, right? So first of all, how many rows do I need if I have 4 inputs? I need 16, right? 2 to the 4 rows, because I have a total of 4 inputs. Then I can just write down what the output is, right? So for example, 0 plus 1 is 1, or 2 plus 2 is 4, okay, or 3 plus 3 is 6. So it's just the binary bit patterns for the numbers. Now the logic gate doesn't know these are numbers. It doesn't care. It's just figuring out, for this combination of inputs, this is the output. But we're interpreting it as arithmetic numbers, right? So there's no magical special adder circuit. It's just another logic function that just takes some combination of the inputs and generates some values on the outputs. Now, if you want to extend this, you could do a 32-bit adder this way, okay? So 32-bit value for A, 32-bit value for B. How many rows would you need in the table? 2 to the 32? It's actually 2 to the 64, right? I have 64 inputs here. I have 32 bits for A, 32 bits for B. There's actually 64 bits of input. I need 2 to the 64 rows of the table. That'd take a bit of paper to write down, a lot of screens. That's a huge number, right? So we don't usually design these big blocks all in one go. We'll break it down into smaller pieces when we're doing the truth tables for it. So let's just skip this guy. This is just showing you how to write out. The idea here is if I want to express a big table like this, I can do it algebraically by looking for where is it a 1 and what combination of inputs cause a 1 on the output, right? So Y is if this is a 1 or this is a 1 or this is a 1, corresponding to these 4 different rows in the table, right? So it's a 1 here if not A and B and C, or it's a 1 if A and not B and C, or it's a 1 if A and B and not C, or it's a 1 if A, B, and C. So these capture the places where this is a 1. You just order those all together, and that gives you an expression for Y. Right? This way of writing it out is called a... So I'm just giving you all these different ways of thinking about a logic function. So this algebraic way is called a sum of products form. Right? So it's a sum of products. Right? So each term is a product of all the inputs, and whether they're true or complement. And so this corresponds to 1 row in the table. And you just write down the rows where the outputs are 1 and all those all together. And that will give you a logical expression that corresponds to the truth table. Yep, question?
Let's say you have like some huge truth table, like that you just kind of like arbitrarily like filled out. Could you be like guaranteed to be able to build a circuit that would match that truth table?
Yes. The question is if you just filled out some arbitrary truth table, arbitrary values, can you always build a circuit? The answer is yes. Yeah, any combinational function, any symbol function that maps inputs to outputs, you can build a circuit for. Okay, any other questions? Now, one reason to write this out, so going from the truth table to an expression, we can do it mechanically here. Just take every row where there's a 1 on the output and write the term here. But this might not be the simplest way of writing down that expression. And so there's whole algebra involved here in how to simplify this. So I can take this expression And for example, what I see here is A is common in all of these three terms, right? And I can actually pull that out here. So A, if I multiply it out, I'll get A, not B, not C, A, B, and not C. These two terms here. And if I look here, this term and this term, this is A and BC. This is not A and BC. So it doesn't matter whether A is true or false. The output's going to be a 1 if B and C are true. Right? People see that? So not A and BC or A and BC. Well, it doesn't matter. If A is a 0, as long as B and C are true, we'll get a 1. Or if A is a 1, as long as B and C are true, it's a 1. So all we need to care about is, are B and C a 1? So now we simplified that expression down to a simpler logic expression. And so this is going to be the strategy to get to simpler circuits. You kind of take the fully written out, fully expanded version of the expression, then you simplify it down using some logical rules. And the fewer gates you can use, the fewer wires you'll need, and the smaller circuit you can build. Okay. So I'll just go over these ground rules again for Boolean algebra. So we use a plus for an OR function. So in Boolean logic, a plus means OR, logical sum. We use product for AND. So we can actually do a dot and say A dot B for multiply, or we just usually leave it out and imply it. As you do in math, AB implies that it's multiplied together, which means it's a logical AND. We use the line on top to mean not for that signal. So this is AB or A or not C. So A and B or A or not C. These are all equivalent expressions for the same logic function. Okay. So the way we can use this is, say we figured out this is the circuit we want. So we sort of sat down and wrote out this configuration of gates, or somebody gave you this set of gates on a napkin and say, go build this circuit for me. You can take this concatenation of gates, turn it into an expression. So y equals, see this is A and B, ORed with A, and then ORed with C, right? That's this expression here. So this combination here represents this gate. This piece here, this symbol here represents this gate. This plus corresponds to this gate. So you're ORing C in with the previous result. So that's the equation you got from the original circuit, but now you can simplify that equation down. First thing you notice is, well, I can pull out A as a common factor here and write, this is AB plus A, which is the same as A into B plus 1 plus C, but this is B or 1. So any signal ORed with 1 is always going to be a 1, right? So just replace that with a 1, and then A ANDed with 1 is just A. So this is just the same as A or C, right? So taking this circuit and just using some algebraic rules simplified to that circuit, which has the same behavior. So for the same combination of input values, I get the same output value from that circuit, okay? And so here are the basic laws of Boolean algebra. So if you manipulate logic expressions, you'll just get very good at applying these. So let's just walk through them. If you take a number and if you take a value and AND it with itself, x and not x is always 0. Because x and not x cannot both be simultaneously true, right? So x and not x equals 0. Whereas x or not x is always a 1. Either x or not x, one of them has to be true, right? So that'll always be a 1. So every time you see this, you can replace it with 0. This pattern, you can replace it with 1. I'll just go through a few of these. So x and 0 is always 0, right? If x and 0, it can never be true. Always has to be 0. Whereas x ORed with 1, that's always a 1, right? Let's have a look at some more of these. So associativity and distribution just work like regular math, okay, pulling out common factors. And this is a very important one, the De Morgan's law at the bottom. So this is a way of moving the knots around. If you have a x and y knotted, so this is an AND, x and y and then knotted, that's equivalent to not x or not y. right? If you just work through the truth tables, you'll see those are equivalent. And conversely, if you not and or, X or Y knotted, it's the same as not X and not Y. Not X and not Y is different than XY, not XY, right? Okay, so this is different than this. Here the inversion is on the output. You AND X and Y, and then you invert the result. Here, I invert X, I invert Y, and then I AND them. Okay? So if the bar goes across multiple things, you're inverting the whole expression under the bar, right? And so here I'm inverting each of these variables individually and then combining them with the AND. Okay? That's a logical convention. Any questions on this? I think a few exercises will help hammer this one home, how these work. So there's some examples. So say y equals ab plus a plus c. I can pull out a as a common factor, ab plus 1. B or 1 is just a 1. A ANDed with 1 is just a. And then we just get a or c. Okay, then we're done. So here's one of the truth tables. So this is then some random assignment of output y given the three inputs a, b, c. So we can go through and see, well, y is true a, b, or a, or c. Okay. Actually, this is just that previous example written now as a truth table. Okay. Right. So notice I could have written this as y equals not a, not b, and c, or y, or not a, b, and c, or a, and not b, not c. I can go through to the sum of products form, but the sum of products form might have many entries, which should all be simplified down to just a or c, right, in the end. Okay. Okay, clicker time. So basically you have that logic expression there, so just simplify it down to one of a through e. Question? Oh, the dot is just a multiply. Just make it clear. Yeah. Yeah, that's not actually necessary. It can just be not a, b, c. And remember the bar, everything under the bar is first calculated, then inverted, right? So the bar applies to everything underneath it. Okay, most of the votes are in. Let's have a look. Quite a spread there. I think I'll give you another few minutes to work on this. Okay, I'll give you another 5 seconds to register your vote. Okay, so looks like most people got it right. Yeah, and yes, it was E. So going back to this, what you can do is start, I'll do it the long way first and then show you a quick way. So the long way is, well, I take this not on B, C, this then becomes not B or not C. So I have not A or not B or not B, C. I can then put a not across all of those. Then I could also take the not out, so then it'd be not A or B, C, which is the opposite of this. So it's either A or B, C or not A or B, C, and so it's always true. That's the long-handed way of just stepping through the steps. Or so you just look at it and say, well, if either E or A is true or B, C is true, if I didn't have this and it was just not A, it would obviously be 1. The only time it's not A is when these are false. When these are false, this guy's true, so it's always going to be a 1. So yeah, Z equals 1. So you just have to practice on working through this kind of algebra. So in the news, if you guys have been seeing this, there's a Russian security firm. So another reason to do hardware is because you can never trust pure software systems, and even hardware, maybe. The Russian security firm claims U.S. spy agencies have been secretly inserting code into disk drive firmware to snoop on foreign countries' computers. So this attack is inside the disk drive firmware. And so when they ship disks off to some, or when some country buys disks from somewhere and they plug the disk into their computer, it gets infected through the firmware on the disk drive. This apparently has been used to snoop foreign computers. But also, a lot of high security installations don't allow you to connect your computers to the internet at all for fear of being attacked. But apparently, even in these cases, apparently the NSA has been shipping hardware with little radio receivers. So even if the machines are not connected to the internet, they can beam stuff into the computers and infiltrate hardware that way, along with radio broadcasts. Or they just put stuff on USB drives, and one standard trick people do is they throw USB drives in the parking lot of some company here or someplace. Somebody picks it up and says, "What's on this USB drive?" And they plug it in the machine and go, "Oh, it's just empty. I can use that." And they're infected. So there's people who are careful with security never let other people plug USB drives into their machine for lots of reasons. So hardware is definitely, we need a lot better security in our systems. That's a real big hole right now, but this is kind of tinfoil hat stuff, but actually it turns out it actually is going on. This kind of stuff happens all the time, apparently. Okay. All right, let's keep going. So signals and waveforms. I've kind of alluded to this a little, but just wanted to go over this a little bit, give you a better idea what's going on. So when you build some kind of circuit, it's, logically it's very clean. There's ones and zeros coming in, the ones and zeros going out. But these are physical things. They live in, and what's exciting about architecture is where you connect this sort of abstract computer algorithm stuff with real physics in the real world and make physics actually do computing. Part of that you have to cope with all the variability and irregularities in the real world. And in particular on those signals we're sending around, they're not perfect 1 volt signals and perfect 0 volt signals. They're not like 1.00000 volts. They're sort of 1 volt give or take a bunch of noise. And so signals have a lot of noise on them. Another thing is that when you're connecting things with wires, it takes finite time for a signal to propagate down the wire. And so you can't instantly signal a 1 or a 0 to the other end of a circuit. It takes some time to get there, right? And so there's delay in waveforms. They're kind of noisy. And this is kind of life. And what's amazing about digital logic is we can work around these physical limitations and build very reliable machines. So one of the ways we do this is this idea of a synchronous system where we have this clock that's beating regularly, and the clock tells us when it's a good time to look at the signals, right? Because sometimes in the middle, the signal's not quite ready yet. You don't really look at it yet. But you want to make sure when you do a circuit design that when the clock strikes, that you want to, then is a good time to actually look at the results. Another thing is, this is sort of, you should be aware of, when you have multi-bit signals, like say the input to an adder, in this case I have a 4-bit signal, x0 through x3. These are carried on separate wires. Every wire carries 1 bit. It'd be a 0 volt and a 1 volt for a 0 or 1. And then it's just an abstract grouping that you do mentally, saying, oh, these 4 signals together constitute this value x. And so these 4 voltage levels, if I read them all at the same time, I treat that as the value 5, right? The wire doesn't know what it's doing. It's just carrying a 1 or a 0, right? It's just carrying some voltage. It's just you looking across these that makes this actually mean a 5 or a 6 or whatever. And so over time, we have signals traveling together like this. And as I said, there's always a delay when you go through these circuit blocks. So when you go through some logic gates, it takes some time from when that control input is applied to when the output changes to the right value. Okay, and so you apply the input signals and you hold them steady. And while you hold the input steady, the output voltage will settle to correct 0 or 1 value. When you change an input, for example, the output might have to change from a 0 to a 1. That doesn't happen in 0 time. It takes some finite time to charge up or discharge the output node, change it from a 0 to a 1. And so you see that if I have an adder here with 4-bit inputs and a 4-bit output, at this point in time, I change the inputs from 2 plus 3 equals 5 to 3 plus 10 equals 13. The output doesn't change straight away when I change the inputs. It takes a little bit of time for this to change, right? And this is what we call the propagation delay of the adder, right? It's a real physical thing. It takes some time for the electrons to move around in the circuit, and that's what you're seeing as the adder propagation delay. Just want to go back again to some notation. So when we draw one line like this, it's pretty easy to see it's a 0 or a 1. And we can just draw it as, at the bottom of the trace, it's a 0, the top of the trace, it's a 1. When you have a multi-bit signal like this, you draw the convention like this. We kind of have both the 0 and the 1 line drawn together. Like you have a 0 line, a 1 line here. They're both filled in. This represents the fact across these bits I have multiple values here that can be either 0 or 1. And notice I just draw this kind of crossover where they change, right? So this kind of pattern of showing these filled-in rectangles instead of just a line is common when you have multi-bit signals. Right? So here I'm drawing the same thing. Like these guys all change from, the output bits change from 5 to 13 at this point in time. And I just show these signals, some going from 0 to 1, some from 1 to 0, and so on as I add new values. Right, so there's a finite delay in propagating signals through a circuit. When you get to playing with bigger circuits, one thing you get very familiar with is how do designers look at these waveform displays to debug their systems. Now, this is kind of a small display. You'll get to see, the guys doing big chips actually look at hundreds of waveforms at the same time, and their brains get wired to see the patterns across all of this. One thing that's a big difference between hardware and software, why hardware is hard and software is not, is in hardware everything happens in parallel, right? So when you run a software program, you can single step it, right? You can go one statement at a time, sequentially, and just see the action of each statement as it happens one after the other. So you can just do one thing at a time, and in your head, you can keep track of, that one thing changed. In a circuit, it's a physical system. There are wires everywhere, the logic gates everywhere. In the big chips, you have, a couple billion transistors and an equivalent number of wires, and they're all working simultaneously, calculating something, right? So the whole space is moving, and this waveform view you see here is one way of showing that, right? You see that at one instant in time, many signals are doing something at different places in the circuit. It's a very highly parallel system, right? And that's what you have to get used to with hardware design. You can't single step it. It all moves at once. You can go one clock cycle at a time, but everything is going to move all around the circuit everywhere. And that's why you need this kind of visualization of what's happening in the circuit, right? Now, to help make sense of hardware, we've come up with this sort of design discipline of synchronous digital systems. And what we do is we divide all the circuitry in our hardware into two camps. One is combinational logic, which is what we've been talking about so far. So combinational logic is where the output is just a function of the inputs. So you hold the input steady, then sometime later the output ripples through, right? So if you have some gates at the input, you hold the input steady, they'll produce an output value that might feed into the input of another gate and so on. But as long as you keep the input steady, eventually the output will settle to the right value. So example be an adder. In addition to that combinational circuitry, we also need, to build a computer, we need what we call sequential logic, which is stuff that remembers state, right? And examples of that are memories and registers. So they remember a value and hold on to it for a while, and we can update that state. And the combination of combinational logic plus sequential elements is how we build big computers. So we use state elements to store values. So the registers in the register file, an example, right? So $1 through $31. And memory as well. Cache is the main memory. But we also use state elements to control the flow of information between combinational logic blocks in the system. Okay? And then we use them to kind of hold up the signal at important points and only let them move through when the clock says they should advance. So to show you why we need this, we're just going to use this very simple example. Say we want to build an accumulator. So the function of this circuit is I'm going to take a stream of inputs, xi, and then I want to output the sum I've seen so far. So if you're writing a C program, you kind of write it this way, right? It'd be s equals 0, for I equals 0 through n, increment I, s equals s plus xi, right? So as each x value arrives, say 1 per cycle, I'm just going to accumulate them to build a sum. Pretty simple function. So let's try doing this just with combinational logic, right? So would this work? Say I just take my adder circuit, I have an input here, I take its output and feed it back. Now, would this work? So remember, there's a combinational logic circuit. Well, no. Right, so this wouldn't work because you don't really know. Remember, it takes time for the signal to propagate around this loop, and you don't know when one iteration ends, the next one starts. Right, so the signal is just kind of like flowing around with nothing to control them. The other thing is, well, how do you initialize this? How do you say sum equals 0 to start this thing off? Right, there's no way to do that in this circuit as it is. So what we do is we add a register. So a register is one of these sequential elements, and it basically can hold the value indefinitely, right? And so here's a register. So this register has a reset input that we can reset it to 0, and it has a clock input, which comes from the clock signal, and this register is only going to be updated when the clock, at a clock edge, when the clock tells it to be updated, right? And so the clock signal is this global signal we run around our whole circuit that tells everybody when to move to the next step, right? And so on the edges of the clock are when we actually change things. So here I'm showing the value on the output. So we want this output to go on this clock edge change to x0, x0 plus x1, x1, x0 through xn. Only on these edges. And so we're going to feed in x0 has to come in a little bit before this. So x0 has to come in, be added to the previous value on this register, and then we'll clock this register and update it with the next one, right? So at each cycle, you're taking the previous output of here and adding it through this one using the adder to produce a value that's then going to become the next output, x0 plus x1, right? So this value plus this value flow through the adder to set up the input to this register for the next clock. Then when the next clock happens, you replace the output with the sum of these two. Then you're ready to add on the next one, right? So this register is accumulating between clock ticks, the total sum. So this is our general model for a synchronous system. basically you have combinational logic separated by these registers, and the clock signal is the thing that beats and tells when the registers should move, update their state, and move to the next state. And this kind of acts as a flow control. It stops these signals from propagating all the way through your circuit. They get as far as the register and they have to stop until the clock edge says they can move on to the next phase. You guys in the corridor, keep quiet. Tell them. So, if you have a register, the internals of the register are called a flip-flop. And the reason is because the output flips between a 0 and a 1, and that's why it's called a flip-flop. So the output on each clock edge captures the input and sends it to the output, right? But only at the clock edge, right? So D is the data input, Q is the name we give the output, right? So when D goes to Q, only when the clock edge hits these guys in the middle. This is kind of like taking a picture with a camera. So when you take a picture with the camera, right, you want everybody to stay still, especially if, you know, have a reasonable shutter time. So you have what we call a setup time. Nobody move while I'm about to take a photo. While I'm taking the photo, don't move. You'll blur the photo. Once I'm done with the photo, then you can move again. And the flip-flop kind of works that way. There has to be a period of time where all the signals to the flip-flop are steady. That's called the setup time. Then the clock edge arrives, and they have to stay steady while the clock is arriving for a little bit of time afterwards, called the hold time. So you have this little window where the signals have to be steady. Just like when you're taking a picture, you want people to be steady while the shutter is open, right? And this is how the flip-flop works as well. And so what we call the setup time is time before the clock, when the signal has to be stable. The hold time is the time after the clock, when the signal has to be stable. And then the clock to Q delay is after taking the snapshot, how long before the output is ready to start propagating through the next part of the circuit. So that's the clock to Q delay. So we'll talk about that, more about this next time.